Since this chapter is about visualizing high dimensional data, just like the way we had iris dataset for exploratory data analysis, let's take another dataset here. Of course, your iris dataset was a 4-dimensional dataset, right? Which is not very exciting, which was okay for our exploratory data analysis. But now we want to do data visualization of extremely high dimensions and dimensionality reduction. So the dataset that we'll use is called the MNIST dataset of characters. Let me explain you what it is. So let's go to Wikipedia, our friend always as usual. So it's called the MNIST database. MNIST database has, so MNIST is a very large name here. It's Modified National Institute of Standards and Technology database. It's a database of handwritten digits, right? So I'll show you. First, let me show you some examples. I'm going to this very interesting blog here called, if you see the link here, it's called cola.github.io and it's called Visualizing MNIST. Okay, this is a blog. I believe this is written by one of the engineers. I think he's currently an engineer at Google. This is one of the best blogs I've come across explaining data visualization of high dimensional spaces using the two techniques, using TCA and TSNE that we will learn as part of this course. Okay, I'll follow this blog because it's terrific, and I give full credit for all the content here to Kola. I think that's the name of the engineer who built all of it. Terrific blog. I mean, this is terrific blog. I can just go to about, and it's Kola's blog, Christopher Ola. Yeah, sorry, his name is not Kola, it's Christopher Ola. He's a researcher right now at Google. Terrific blog. I mean, this is probably one of the best blogs I've seen about visualizing high dimensional data and understanding what it is. So I'll provide a link to this page in the description section. And this page is not built by me; it's built by Christopher Ola. Again, just wanted to reiterate that. But it's very hard to redo all of this. So I thought by giving credits to him, I'll reuse some of the great content that he has created. So this content, all the copyrights to the content belong to Christopher Ola. I'm just leveraging it so that students can learn it much faster and much more efficiently. Okay, so let's look at what the MNIST dataset is. The MNIST dataset is basically handwritten characters. So each of these, so this is basically a photograph of a handwritten character. So we have characters from 0, 1, 2, so on and so forth up to 9. We have 10 characters here, right? And these are basically, somebody has handwritten this character and taken an image of it or scanned it, right? This is basically 28 pixels horizontally and 28 pixels vertically. That's the size of each of these images. So each of these images is basically 28 pixels horizontally, 28 pixels vertically, right? This is a computer vision data set, because what we have to do, and we are given 60, so the data set is like this. We are given 60,000 or 60K training data points, right? Where we have some data points for 5, some data points for 0, 4, 1, etc. And we are given 10K test data points, right? So we are given 10K test data points. So we have to build a model using the 60K and test it on the 10K or 10K data set. So for those of you who don't understand what train and test is, don't worry about it. We'll learn it when we learn machine learning. For our case, let's just assume we are given a 60,000 data points. Okay, train and test, don't worry. We'll learn it when we learn actual machine learning techniques called classification. Okay, so don't worry if you don't understand what train and test is. That's perfectly okay. Okay, let's go and write it. So our data set is basically xi and yi. Okay, and we are given 1 to 60K points. Okay, we are given two data sets. One data set is called training, one data set is called test. Don't worry about what the terminology means. Let's just use the train data set. Okay, it's 60K points, where xi, each xi is basically an image which has 28 pixels horizontal and 28 pixels vertical, right? And yi could belong to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It can be any one of these classes, right? So here, if I've written something like 0 here, that will belong to class 0, right? So the task here, that's very important. The objective here, the objective in this task is, given a new image, a scanned image of 28 pixels by 28 pixels, I have to determine whether the user has written 0, 1, 2, 3, or one of these 10 characters. Okay, that's the objective. The objective is to classify the written character into one of the 10 categories, into one of the 10 numeric characters, right? Okay, so that's the objective, right? Now let's go back to the data set just for a second. So given this data set, so we are just using the 60K points here. We are not using the 10K. We'll use them later. Trust me, we'll use them later. Now let's just stick to the 60K points. Now given this image, right, each of our data points is like this. But what did we learn? We learned that xi's need to be data vectors, column vectors, right? That's what we learned. We never saw images. So the first question that comes to your mind is, how do I convert an image, okay, which is 28 pixels on the horizontal and 28 pixels on the vertical? How do I convert it into, so this is what you're calling my xi, right? This is what is given to me. How do I convert into a column vector that I know? This is what I know. This is what I know belongs to RD. This is what I know. How do I go from this to this? So let's see how to do it. Okay. So this is each of my images, and let's see how this image is represented internally. Okay, mathematically. So at the end of the day, any image has to be represented using numbers in a computer, right? So let's see how this is represented right here. So a number like 1 is represented. So there are 28 values here. This is a matrix of 28 by 28 size, right? The 28 rows, so 28 columns and 28 rows, right? That's the size of a data set. Now, given that, let's see what's interesting here. So wherever it is fully black, I have 1 here, right? Wherever it is slightly gray, I have a value which is slightly away from 1. So here I have 0.6, which means it's gray. All these are full blacks. Here it's light gray. This is how 1 is represented internally. Wherever it is white, all these pixels which are white. See, this is, I can draw a grid like this, right? It's 28 pixels by 28 pixels. So I can draw a grid here, right? A very fine grid of 1, 2, 3, so on and so forth up to 28. Similarly, 1, 2, 3, so on and so forth up to 28. And I can take the value in each pixel. If it's fully dark, I'll put a value of 1. If it is slightly gray, I'll put a value between 0 and 1 like this. This is very light gray. This is darker gray. This is still darker gray. And this is full black. If it is white, I'll put a value of 0. Okay. So we have converted now an image. So now what do we have? We have an image, okay, which you have converted into a numerical matrix, a numerical, actually real matrix, right? This matrix is of size 28 cross 28. Again, this matrix is not your data matrix. This is one data point. Don't forget that. This is exactly one data point. Now the question is, since I've converted an image, okay, into a data matrix, how do I go to a data vector or a data point? This is not a data matrix. This is not, let me write it. This is not your data matrix. Okay, this is not your data matrix X. This is just a matrix representation, of your image. Now let's see how we can convert this matrix of pixels into a vector. Okay, that's very, very simple. That's extremely simple. What we do is, so given that we have 28 pixels by 28 pixels, we do something called flattening. So we do something called flattening. Flattening basically says, okay, let me draw it here so that it's much more clearer for you. Okay, so let's assume I have a matrix which is 1, 2, 3, 4, 5. Let's assume I have 5 columns, and let's assume I have 5 rows, just for simplicity, because it's easier for me. Let's assume I have a value of 1, 2, 4, 6, 8, 3, 2, 1, 8, 1, some numbers like this, okay? 2, 1, 6, 8, 4, 3, 2, 1, 8, 1, 8, 2, 4, 2, 6, 8, 1, okay? So how do I convert this into a column vector? So we do something called as flattening, okay? Flattening is basically, you take each row, okay, you write it 1, 2, 4, 6, 8. So this is done, this is done, this is done, this is done, this is done. Then I take the second row, 3, 2, 1, 8, 2, done. Then I take the third row, 2, 1, 6, 8, 4, so on and so forth, right? I just build a long vector by looking at my image matrix. This is my image matrix, right? I'm just going row wise. First I finish the first row. Let me change the color here. First I finish the first row, then I go to the second row, right? Then I go to the third row, then I go to the fourth row, then I go to the fifth row. You can also do column wise. Nobody's stopping you. You can do first column followed by second column, so on and so forth. You can do row flattening or column flattening. Okay, this is basically row flattening. Now, if this matrix is 5 cross 5, what is the size of this vector? How many elements are there? There are 25 elements, right? This vector will be 5 into 5 is 25, right? This will be 25 rows and 1 column, isn't it? So in our data set, we have 28 by 28 pixels image, right? So 28 into 28. So what we have here is each of our image is 28 pixels by 28, which means that 28 horizontal pixels and 28 vertical pixels. So I can convert this into a data point. I can convert this into a data point, which is a column vector, by just doing row flattening, right? I can simply do row flattening or column flattening. Anything is all right, which means I go finish first row, then I go finish second row, then I finish third row, so on and so forth. This vector will be, what is 28 into 28? I think 28 into 28 is 784, right? So this vector will have 784 rows and 1 column. So by just using row flattening, so let's go back here. Okay, so this is what my actual image is. My image had 28 horizontal pixels and 28 vertical pixels. How do I convert into a matrix representation of an image? By saying that all the black points will be 1, all the gray points will lie between 0 and 1, all the white points are 0, right? So on and so forth, as we saw here. Now after I do this, I basically do row flattening or column flattening. And now I get a 784 cross 1 dimensional vector for each data point. Now how will my overall data set look like? Let's go through that. My overall data set, capital X, now is, so each image or each data point is now 784 dimensions, okay? Which means I have feature 1, feature 2, feature 3, so on and so forth. F784. See, if I take each pixel value as a feature, I can take it, right? That's the simplest way to represent. And I have 1, 2, 3, I have 60k points. So my matrix here is n cross d, where n is 60k, d is 784, right? Now here, this xi transpose for me belongs to R784, right? So this is the total data set. This is the total MNIST data set. Of course, I also have a y here, okay, which is n cross 1. For each xi here, I have a yi, and yi, as we know, belongs to the set. It could be any one of these characters, right? Because your whole MNIST data is only 10 characters, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So given this data set, now we want to visualize this data. Now here is the fun part. So now we have a 784 dimensional data set. Okay, we struggled even to visualize 4-dimensional data set. We saw, right, when we have 4, 5 or 6-dimensional data set, we can use things like pair plot. But as soon as this dimensionality increases, even when it becomes 10, pair plots become almost useless. Now here is the most interesting thing. How do we now visualize a 784 dimensional data set? This is the beauty of machine learning. We will use simple linear algebra, very, very simple ideas to visualize the 784 dimensional data set. Before we go and learn techniques like PCA and TSNE, I want to show you the results, which are mesmerizing. I want you to show the results. Of course, I'm running through this, but I'll explain you all of the topics here. Okay, let's see. I want you to show. I think. Let me. I have a nice visualization here. I'm just trying to pull it up. Okay, the best. Let's go to the bottom of the page and let's see. There are multiple techniques here. We are learning the two most important techniques, PCA and TSNE. TSNE is literally the state of the art. Okay, TSNE stands for T-distributed stochastic neighborhood embedding. Don't worry about the names. So let me just run this. Okay, I'm just running it. So here, this is the final output. How we reach this output, I'll explain you. I promise you, I'll surely help you through this. This is the algorithm running right now. Here, each dot here represents a data point. Each dot here represents a 784 dimensional data point Of course, we can't visualize 784 dimensions, right? We are projecting into 2 dimensions. My x-axis here is dimension 1. My y-axis here is dimension 2. So what I've done here is I have taken a data which is 784 dimensions, and I have converted this data into 2-dimension data so that I can easily visualize. Okay, this is what I have done. Each point here corresponds to one of your x's, each visual point here. So I've taken 784 dimensional data and transformed this using an algorithm called t-SNE. We will learn what t-SNE does internally. Okay, I just want to motivate you with an example of how it will be at the end. Okay, we convert into 2-dimensional data set, and the color code for each data point is the class label. Okay, let me show this to you. Okay, let me show this to you with an example. Okay, so I'm just going on this page as my mouse pointer moves. All these are zeros. This is a zero like this. These are all images that it's showing. So all your red points are zeros, as you notice. Okay, so what about your these points are sixes. Your blues are sixes. Now you might wonder, why the heck is the blue point there? Why the heck is a blue point there? If you point to the blue point there, right? It looks, so even though it is 6, it actually looks more like 0 because somebody didn't put the tail to your 6 properly. Similarly, this 6, it looks more like 0 than 6, right? That's why so that's why this looks more like this. Even though this is 6, it looks very much like a 0, right? It looks very much like a 0. So it looks very much like a 0, right? That's why it has put this point closer to so all your red points are zeros. If you notice, all your zeros have come very close to each other. Okay, all these light greens are your 2s, right? All these blues are your 6s. All these purple colors are your 8s. Okay, your dark greens here are your 3. Your browns are 1. So what they have done is they have applied t-SNE, okay, to transform your data from a 784 dimensional data set to a 2-dimensional data set. Okay, this is the dimensional reduction, where I'm taking a data which is extremely highly dimensional and I'm converting it into a very low dimensional space. And now when I visualize this data and when I color these points based on my YAs, it looks very logical. All my zeros are somewhere here, right? All my 6s are mostly here. And a 6 that looks like 0 is grouped with zeros. So this gives me a lot of intuition on how the data is in the 784 dimensional space. So this is the final outcome after running t-SNE. But what happens internally, all the mathematics we will learn. I just wanted to motivate you with an example. So this is the MNIST dataset, which we will use for dimensional reduction techniques. Okay, we will run through all of them. We will replicate these results. By the way, we'll replicate these results in our Python notebooks. But for teaching, using Christopher Ola's notebooks are much more useful because very, very interactive. All of this code is written in JavaScript. Beautifully interactive stuff. So even though this is 2, it looks closer to 0, and hence it was grouped. It's closer to zeros than 2s. All these are 2s. Okay, this is brilliant visualization. Okay, I promise you, as part of this course, in the next few topics, you'll learn all about t-SNE. And we will use the MNIST dataset. We will use the MNIST dataset for understanding high-dimensional data visualization and dimensional reduction. Of course, for all of your high-dimensional data visualization, we have to reduce the dimensions of the dataset so that it's much more understandable. Just like this. Here is a proof. I'm taking a 784 dimensional dataset and putting it into 2D, and the visualization is terrific.